We're going to talk about absolute convergence and the ratio and root test. So first of all, let's think about the series. So we have a series here, right? A1 plus A2 plus A3. And then keep on adding. So you sum up the term. So that's called the series. Now, if you put the absolute value over here on every term of the series, and we're going to get a new series. So this is the new series. The new series is resulting from putting the absolute value on every term of this original series. So if this series that has absolute value on every term here, if it converge, we'll say that this series here converge absolutely. So now we say something converge absolutely, right? No question about it. Absolutely, right? That's a very strong word, right? So if this converge, that means this series converge absolutely. Okay. Now let's try some example. Okay, let's look at this series here. This series over here is it alternating series? Can you guys tell me? Yes, it is, right? This part here is always positive. This part here is the alternating sign. Okay. Now this is the original series, the series without the absolute value sign. What happens if I put the absolute value on every term? Take the absolute value on every term. What will be the resulting series over here? It's all positive. And then what do you do with the alternating side? Do you just drop it? Right? Can you just drop this one? Yeah? Right? So if you put the absolute value on every term, then the alternating side, you can ignore it, right? So the resulting series will be what series? It's a series, what should I put here? 1 over n squared, yes, okay? So it's always positive, right? Okay. This series here converge or diverge? Converge, why? Yes, because p is greater than 1, right? Yeah. P is greater than 1. It is a p series. When p here is greater than 1, it converges, right? So p is 2, so it converges, okay? So that one converges, okay? So let's write down. So we know that it converges. Now, according to this definition above, if the series that when you put the absolute value on every term here, if it converges, then what can we say about that series? It converge absolutely. Huh? So it converge absolutely. Okay. Let's see if I can do this. So converges absolutely. Okay. So and I heard someone say the series also converge. Right? Actually, that was true. Right? That is true. We're going to show that one. So here the series converge absolutely. So does it mean that the series itself is going to converge? It turned out to be true. Okay, it's actually converge absolutely. It's actually a stronger kind of convergence. Okay, even stronger than just convergent. It's converge absolutely. Okay, it's very strong. Okay, when you say something absolutely, no question about it, right? It's just actually a stronger kind of convergence. Okay, okay. Now let's look at another example. Look at this example over here. This series here is an alternating series. Converge or diverge? Okay. Without the alternating sign, it's a divergent, right? Without alternating sign, what kind of series you get? Yeah, without alternating sign, it's a harmonic series, right? Which means that if you put the absolute value on every term over here, and then you can drop this alternating sign, and you have this 1 over n over here, right? Okay, that series here is a harmonic series, and it diverges, right? Okay, so it diverges. Let's just put diverges, because it's a harmonic series. But with the alternating sign, it's a different story. Okay. Last time on Tuesday, we talked about the alternating series test, right? Do you guys remember that? What was the alternating series test? If Bn, Bn goes to 0. Yeah, we check two conditions, right? So if Bn here goes to 0, okay, number 2 and 3, then plus 1 is less than equal to Bn, right? The series, the alternating series here is going to be convergence, right? And I know we actually generalize that, right? So let's check this one. If this one here go to the yeah, is the EM epsilon less than equal to yeah, setting by the two, right? So what can we say about this alternating harmonic convergence? We actually generalize it now, right? And we say that any alternating PQ is going to converge, right? So this is going to be convergent by alternating series test, by AST, alternating series test. Okay. All right. Now we have this series is shown to be convergent. However, if you put the absolute sign over here on every term, it diverges. Can we say that series converge absolutely? No. If it converge absolutely, it has to be this one here also converge, right? But the series here does converge, right? It does converge. So we see the series here converge conditionally. Okay, conditionally. So it converges conditionally. Okay. So it is not absolutely. Okay. So from the two examples, you can see that the converge conditionally and converge absolutely. This one here is actually the stronger kind of convergence. And this one here is a weaker kind of convergence. Okay. This one doesn't converge absolutely. So I'm going to put it over here just to compare the two concepts. What does it mean converge absolutely? And what does it mean converge conditionally? And what does it mean just converge? Okay. So converge absolutely means that the series and also the series with the absolute value over here both converge. Okay. If they both converge, then it's converge absolutely. Okay. So converge absolutely is the stronger kind of convergence. This and then both converge. Okay, absolutely, no question about it. Okay. Then what about conditionally? Conditionally, the series itself converge, but if you put the absolute value over there, they actually diverge. Like the example we have done over here, the one above. Okay, this one. So it converge. However, if you put the absolute value over here, it actually diverge. Okay, so conditionally. Okay, all right. Well, what about convergent? Convergent, it just says the series converge. It doesn't say anything about the one with the absolute value. All right, and now we have this theme over here. So it says that if it's absolute convergent, then it implies the series converge. So this one converge actually implies this one converge. The proof of that is actually not long. Then how do we prove this? So I start with the series converge absolutely. Okay, and what does it mean? That means that this equal to a finite number. Okay, and I'm trying to prove that this is also equal to a finite number. So what will be the idea? So you try to relate this one with this one. How can I relate? Well, I can relate it this way. I can express this an as this, subtracting this. So you add the absolute value here, and then you subtract this back. So you're not adding anything actually. So this should cancel, you should get like this. So the math we always do put something in and then we take something back. So this is some that kind of trick. So that way I can relate those, right? Relate that with this. Now we're going to take the series on both sides. So the series with an over here is the series of this subtracting the series of this. Now this one here is convergent. Why? Why this one here is convergent? How do I know this one converge? What does it say? It says here, right? It's absolute convergent, right? So this one converge to a finite number, right? Okay. What about this? What about this one? Do you think it converge? Probably. Okay. So if I can prove this one converge, that means it's equal to a finite number. Then finite number subtract a finite number should be a finite number. Then I should be able to prove this one is convergent, right? So the problem here is going to reduce to proving this one equal to a finite number. It converges, okay? The way to do this, we're going to use this comparison theorem. So we're going to think about this one here, bounded above by this, bounded below by this. So this one plus this one is always positive, right? This is always greater than this. And now if you replace this one here by the absolute value, this one certainly is less than or equal to 2 times the absolute value over here. Okay? So that is going to be bounded below by 0 and bounded above by this. But for this one, you can take out the 2 because this is a scalar multiple, constant multiple. So take out the 2 in front of the summation sign, the sphere. Then you have 2 times this. But we already know this one here converge. 2 times that will also converge. So this is convergent, this is convergent. We remember last time we talked about if the bigger series converge, right? Remember we think about the airplane, right? So the bigger positive series converge. What can we say about the smaller positive series? It also converge, right? So this one converged. Now after you put that this one here converge, then that means this is a finite number. And then subtract here, this is a finite number. So that should be equal to a finite number. So that series will also converge. Now, after all this, I think the most important for you is to remember the result here. So absolute convergence implies convergence. Okay. Now repeat after me, everyone. Okay. Absolute convergence implies convergence. Okay, good. All right. Does it go the other way? No, it doesn't. Okay, great. So it is a stronger kind of convergence. Okay. Now let's try to use this one. The first example, looking at this, do you think this is alternating series? No, I say it's not alternating, right? Because the sign over here is not plus minus, and sometimes could be plus minus and minus plus and minus. The sign here is not alternating like that, right? So we cannot use the alternating series test. Can I use the comparison test? You would like to, right? But for comparison test, we only work for series has positive trend, right? Remember the side here? Remember the comparison test? The trend has to be all greater than or equal to 0, right? It doesn't work for series that sometimes negative, sometimes positive. This one doesn't. But how can I make the trend to be all positive? Yeah, right. So we're going to put the absolute value over here. Put the absolute value over here. And then the result here, the trend will be all positive, right? Because the absolute value. Okay? Now we can use the comparison test on this one. And what would you like to compare to? Which series? Whenever you see sine and cosine, you try to compare it with what? 1, right? Let's replace the cosine there by 1, okay? So compare with 1 over n squared. Yes, you got it. Okay, good. Compare it with this. So let's compare with that one. Okay. Now both series here has positive trend, right? Okay. Which one's bigger? This one, or this one? Which one is the one above? This one? This one bigger? Yeah, it's bigger. Because cosine is always less than or equal to 1, right? So this is bigger, right? This is the bigger one. So now this is bigger. What happened to this series that has bigger positive chain? Converge or diverge? Converges. And why? Because it is the P series with P equal to 2, which is greater than 1, right? So it converges, okay? So if the series with bigger positive chain here converge by the comparison test, what can I say about the series with smaller positive chain? Also converges, right? Okay, good. Huh?
What's an absolute value in the
Here, the absolute value? Oh, I'm just talking about the series with the absolute value. Oh, your question here is,
why is there an absolute value?
oh, because if you want to use a comparison test, both series have to be positive chain. So if sometimes the chain is negative, sometimes positive, it doesn't work. The comparison test only work. Okay, look at the picture here. Comparison test only work when the series all the chains are positive. Okay, so if the bigger positive series converge, then the smaller positive series will converge. Then if this one over here is like sometimes come down, up, come down and up, right? Or down over here, then no. Okay, so when this one, imagine that this one here, the trend goes down here, down here, down here, down here, something like this, then it's not going to stay any stability, right? So both this one and this one have to be positive. Because if it has negative, sometimes it can go really negative, right? And this one can converge, we say nothing about this series here, right? So in order for the comparison test to work, both this one and this one, the chain has to be positive. In other words, it has to be above this x-axis. Okay, so that's why we put the absolute value over there. So then to ensure that the chain over here will be positive. Okay, so the absolute value here. So the biggest positive series here converge. Then the smaller positive series can also converge. Okay. Now, Diego is saying, well, but before you didn't have this absolute value, right? This one here doesn't have the absolute value. So all you just said that here is the series with the absolute value over here converge. How can I know this one here without the absolute value here also converge? How can you know? If this one converge, is what kind of converge? Absolute convergence. So that's the stronger kind of convergence. So converging implies what? Convergence, right? So we just said that, I repeat. You repeat after me, right? Absolute convergence implies convergence. So if this one here converge, then this one converge. So in other words, that if you have the chain here, if you put the absolute value there, if the series converge, then without this absolute value here, that series also converge. Okay, so this gives you an idea of sometimes when the series that you trying to find, see convergent or divergent, if the series is like this, sometimes positive, sometimes negative, and it's not an alternating. Okay, then what happened? You can actually do the trick. The trick here is to put the absolute value on every chain and then use the comparison test. And if that series converge, then without the absolute value, will also converge. Because this is absolute convergence and this is just the normal convergence. So absolute convergence is the stronger kind, the convergence, and you will imply convergence. Okay.
But shouldn't it be convergence at absolutely?
Huh?
The one below.
This one? Oh yes, good point. So this one converge. I can actually make it stronger. Converge actually absolutely. I hope I saw this right. Okay, so it converge actually absolutely. You got it. Yeah. But absolute convergence actually implies convergence. So this is the strongest convergence you can get. Okay.
So basically, that will not be
Yes. Yes. Yeah. So when we put the absolute value here, if it's convergent, just converge absolutely. So it's absolute convergence. So this one here, let's say that this is the absolute convergence. So it implies this convergence. We got it. All right. Now we're going to go to the ratio test. So now we have this. Okay. This is the series, right? Let's look at the end turn and the turn after that. And what we do here is we're going to look at the ratio. Okay. It says it's the ratio test. So look at the ratio of this one over this one. So the next turn over the turn before that. Okay. So look at the ratio. This ratio over here. And the absolute value of the ratio. So that. And that angle to infinity. If the limit of this ratio here is less than 1, okay, so suppose we go to a limit and say equal to L, and that is less than 1, then we can say that the series converge absolutely, okay, which is the stronger kind of convergence. And if it is greater than 1, if the limit over here is greater than 1, okay, including it go to infinity, if the limit is infinity, then the series diverges. And if it's equal to 1, okay, if it's just 1, then we have no conclusion. And we have to use other tests. Okay. So this is the ratio test. Now, from this, I think I'm not going to go through the proof, but however, I'm going to give you the idea, some explanation. For this, does it remind you of the, let's think about that, compare that with the geometric series. So what does this one here mean? Okay. So an plus 1 over an. Okay. For geometric series, an plus 1 over an will be always equal to the common ratio, right? Okay. So let's compare that with the geometric series. I'm going to do this. Okay. All right. So for geometric series, okay, every time you multiply by the common ratio R, geometric series converge even only if what happens to the common ratio. Absolute value of R is less than 1, right? Yeah, you got it. Okay. So like that. Now you want to think about this one here, like this. And this is the absolute value. Right? This is kind of like the common ratio over here. Okay. So the absolute value of the common ratio, if it's less than 1, then it converges absolutely. Okay. Because think about this. an plus 1 over an, right? So the next term over the one before is kind of like a common ratio. And they behave in the long run. So when n goes to infinity, the next term over the term before and it's about equal to a number that is less than 1. So that means at the end, then it's kind of like a geometric series at the end. So every term is multiplied with a number that is a little bit less than 1, okay, and then is less than 1 to get the next one, and then multiply by a number that's less than 1 and get the next one. So in the long run, it's almost behave like a geometric series, okay? So therefore, it's going to converge. It's going to converge when this one here is less than 1. So compare with the geometric series and try to understand that, okay? So then we understand this one, less than 1, it converge absolutely, okay? The absolutely actually come from the absolute value sign over here also, okay? Now, and then if it's greater than 1, Well, also think about comparing to the geometric series. So that means in the long run, the end of this series behave more or less like the geometric series, except the absolute value of this R is greater than 1, so then it's going to diverge. So over here, it's going to diverge, okay, like that. So we understand this one and this one by thinking about that comparable geometric series. But what about equal to 1? How come it has no conclusion? Why? All right, so let's try to use the ratio test on this two, on this two P series. Okay. For the first one over here, what's an plus 1 over an? Let's work this out. Yes. Okay. Divide by 1 over n is the sum as multiplied with n. So this is the sum equal to what? N. You got it. As n goes to infinity, what does it go to? Yeah, it goes to 1. You got it. Good job. Okay, so this n over here, right? You look at the dominating term, it goes to 1. Okay, good job. So it's L equal to 1. The limit of that is 1. Okay. Let's look at the other one. Okay. This an plus 1 over an. What do you get? 1 over. Okay, good. As n goes to infinity, what does it goes to? You got so fast. Good. Use a shortcut that we talk about, right? You look at the dominating term, right? The n squared. So it goes to 1 also. Okay. So both of them, the limit over equal to 1, which is this case. So what do you know about this series? The first one. It diverges, right? What about the second one? This one. It converges. Okay. Because the P series test, right? Okay. So both of them go to 1, but one diverge, one converge. So it doesn't tell you the series converge or not when the limit over here is equal to 1, right? So there's no conclusion. So what should we do if there's no conclusion? Use other tests, okay? So if there's no conclusion, then you just use other tests. Maybe, what other tests you find them before? Integral tests? Comparison tests? Telescoping, P series, geometric, yes. Hey, don't forget the easiest one. What's that? Test or alternating series test also. Also, test for divergence. Yes, good, very good. Okay, good job. You can remember all of them. That's great. So use that. Okay. All right. So here you say I put a weak mark over here. So both this one and this one have L equal 1. The limit of this ratio equal to 1. But when you went the other one diverge, so do not use the ratio test on P series. Okay, do not use it because all of them is going to turn out to have 1 for that limit of the ratio. So you don't want to use it. Okay. So if you see a series that's kind of similar to the P series, do not use it. Okay, don't use it on a series that's similar to a P series. So if the pattern kind of similar to the P series, then don't use it on that. Okay, because you're going to get the limit here equal to 1. Okay, and I think in the past my student asked me a question about this one. This one over here, as n go to infinity, what does it goes to? If you look at the dominating term, it's not 4 over 7 because this one here is 4 to the n, 7 to the n. So in the long run, it's a 4 over 7 to the n power. As n go to infinity, think about you keep on multiplying Okay, think about this. Maybe I should write it the long way. So you're going to have 4 times 4 times 4, etc. And then down here you have 7, 7, 7, right? Okay. But the more time, oh, are you able to, you can use this. I don't need this. Okay, you guys can have this on this side. So the more time you multiply, right? Each one of them is less than 1, right? The more time you multiply, does it get smaller and smaller? Right? Like 0.5 times 0.5 times 0.5, etc. Right? It go to 0. Okay. So it go to 0. It's not 4 over 7. Okay. So this one here is not a polynomial. It's actually a exponential function. So 4 over 7 here, and when n go to infinity, that go to 0. Okay. So it's not going to 4 over 7. Okay. Okay, good. All right. Just some side note. Now let's over here say, oh, when do I use ratio test? Sometimes we're looking at the series. You know why the way use the ratio test? Ratio test is actually one of the easiest one to apply. Okay, so you want to see the pattern. When do we use the ratio test? Something like this. We might use to use the ratio test. So I say, if the an here involve n to some power. For example, here, n to the third power, okay, n to the third power, right? Or a number to the n power, like 3 to the n power, like that. Okay, you see this one? N to a power, or a number to a power, okay? Then you want to use a ratio test. The reason for that is because it's going to have a lot of canceling, and it's easy to find the limit. Okay. Do you want to give a try? Okay, I'll do the first one. Maybe you guys can do the second. Okay. And try, we can try. Oh, actually, the second one is harder. Okay. I'll do it together. Okay. All right. So we're going to let an to be what? An to be, yeah. Yes. Yeah, that's an, right? So this is an. What's an plus 1? To the n plus 1 power. Yeah. N plus 1. Right? Yeah, you got it. So basically, you just replace, every time you see n, you're going to replace by n plus 1, right? So you got this. Okay, so the ratio test. Okay, let's look at the ratio. So we look at the ratio, the absolute value of this ratio, okay? Now, we can ignore the alternating side because the absolute value there, you don't need the alternating side there. So we can just we're going to take this part, right? Take that part. So an plus 1, we'll just take this one, take away this one because the absolute value over here. So we get n plus 1. Now dividing by an is the same as multiply by the reciprocal of this. So what's the reciprocal of this? Yeah, you got it. Good job. Okay. Okay, you fast. All right. So it just go ahead and multiply the reciprocal of that an. Okay. I took away the alternating sign because it doesn't matter because the absolute value. Okay. Now we can do the canceling, and that's the reason you see that when you have you have this kind of pattern, a lot of canceling can take place over here. That's why you use a ratio test. Okay, let's see how we cancel. Then yes, very good. So this one here, remember this one here is 3n times 3, right? So it's going to cancel out the 3 to the n power. Yeah, you got it. Good job. Okay. All right. So let's write down. So that should be, well, because n here is always positive, I actually can drop this absolute value there. So I can just write it down as 1 over 3. And I'm going to group these two together. Okay, this one. Oh, Okay, this one and this together. Okay, so these two together, I will have, what do I have? I have n plus 1 q over nq, right? Okay. The reason I can drop this absolute value over here is because they are guaranteed to be positive. So there's no need to keep the absolute value there. Okay. Now we're going to take this as n go to infinity. So the n go to infinity, what does it go to? Someone say, Diana say 1. Well, which part go to 1? This part can go to 1, right? Okay, so this one can stay as 1/3, right? So it's 1/3 times 1, so that goes to 1/3. Yes, you got it. Okay. So this one over here goes to, this one goes to 1. So 1/3 times 1. So that's 1/3. 1/3. Okay. Yeah, it's 1/3. Okay. It goes to 1/3. Okay. All right. Some people say, how do you know that one go to 1? Well, the way, yeah, there is the same power, right? So you see, this is n to the third power. This is n to the third power. Yeah, same power. Yeah. Another way to do that, you can write it as n plus 1 over n to the third power. Okay. And inside here is go to 1. 1 to the third power is also. Okay. Good. Good job. Okay. Okay. Now, we found that this ratio, the absolute value of this ratio goes to 1/3, which is comparing to 1, it is less than 1. What can we say about that series? Converges? Yes. Let's go back and revisit, okay? So what does the ratio test say? It says that if that limit is less than 1, then the series not just converges, it actually converges absolutely. Okay, so you can actually put down absolutely. Okay, that's even stronger. So, so let's write down. Okay, this series over here converges. Okay, and if you want to be even stronger, it's absolutely by the ratio test. Question. Now you see that why when you see the pattern, right? You see this an here involve n to some constant power or constant to or positive constant to n power, then you want to use the ratio test because it will be easier to find the limit of this ratio, limit of the absolute value of the ratio. And so that would suggest that we use the ratio test. Okay. So ratio test is actually quite convenient to use. Okay. The pattern. The next pattern here is this. If you see n factorial, then use ratio test. Or n plus 1 factorial, okay, or n plus 3 factorial, okay, use ratio test on that one. Okay, so that's another pattern. Would you like to try this first? I'm going to pause the recording and let you try this. So over here, we replace the n here by n plus 1. So we got this. This is an plus 1. And then times we sit for an. So times n factorial on top and to the n power down here. And after that, let's regroup this. Let's think about what happened to this one and this one. Okay, n factorial over n plus 1 factorial. N factorial is the sum is 1 times 2 times all the way to n. What about n plus 1 factorial? 1 times 2 times all the way to n, and then one more factor, which is what? N plus 1, right? So when you divide them, what gets canceled? You're going to cancel out this, right? And leaving you with what? 1 over n plus 1. Yeah, you got it. Good job. Okay, so 1 over n plus 1. Okay, so now what happened? So that is 1 over n plus 1. Okay, now let's say, what about this one and this one? This one here with this one over here. Okay, let's put it there. So n plus 1 to the n plus 1 over n to the n. I usually like to put them, the one that has similar form, I want to put them together to as a quotient like this, compare. And then this two, I'm going to put them together as a quotient like this to reduce. Okay, so what about this one? Now, if both of this have to the n power, then I can put them under the parenthesis, right? So what do we know about this? This is n plus 1 to the n power multiplied with what? N plus 1, yes. Okay, so then this is n to the n. Now what happened? This one here is the same as this one, right? Isn't it? It's the okay, good. And then we left with this. This one here and this one here, do they cancel? Otherwise?
Yes.
Yeah, they cancel. Okay. So these two cancel. Okay. So the result here, what should be the result then? Should be this, but this part here will cancel. Because this one and this one cancel. So this one here I'm going to modify. It should be just no more this, right? We cancel already. Okay, it's n plus 1 over n. Okay, so cancel out. Okay, so you got this. Because do you think this is always positive? Do we need the absolute value over here?
No.
We don't, because it is positive already, right? So we can actually drop the absolute value. So it will be this to the n power. But looking at this, looking at that one, okay, and look at the sign that I put in. Oh, I read it so small. This one here is what I have over here. It's so small. Okay, this one here, n over n is just 1, right? Okay, and plus 1 over n is 1 over n. And then here to the n power, so this is this difference. What's the limit of this as n goes to infinity? I put it over here. This is final. The limit of that is e. Okay. As n goes to infinity, that goes to e. Is e greater than 1?
Yes.
Yeah. E is about what?
2.7.
About 2.7, right? So it is greater than 1. So the series converge or diverge? It diverges. Okay. So the series diverges. By what test?
The ratio.
By the ratio test. Okay. By the ratio. You got it. Good job. Okay. Because the limit of the ratio goes to 1. This one is a little bit tricky because it involves factorial. And just remember, if sometimes you don't see it, try to write it in the long form and you see what kind of canceling happens. Okay. And also you need to recognize to write them as the same power. M power, you can group them like this. Okay. And this one and this one multiply become 1, so cancel. Okay. And you also have to remember this number right here. Okay. So this one is a little bit tricky. Okay, so you did a good job. Okay, thank you. Thank you for your participation. Okay, you will have more chance to increase the participation. Okay, now, there's some side note over here. This, instead of 1 here, if it's replaced by 2, it's actually e to the second power. Okay, I think we pulled this somehow early in the semester. Okay, but just for your interest. Okay, the next one over here, we're going to do the root test.
the root test is very similar to the ratio test.
So you're going to look at the n root, okay? N root of this absolute value of an. As n go to infinity, also three cases. If the limit is less than 1, then the series converge absolutely. If the limit is greater than 1, including the go to infinity, then the series diverge. And when it's equal to 1, then we have no conclusion and we have to use other tests. Okay. I'm not going to go into the proof of this, but you can try to put this and the ratio test together to remember. So they're very similar over here. Okay. How about we try to use it? Okay. So let's try to use this. And sometimes you say, well, when do I know I use the root test? If I look at this series, how can I tell I will use it? So this one here, do you think you're going to use the root test? Look like the an here is this to the n power. If you take the n root of this, what happens to the n root and the n power? They cancel, right? So that would suggest that the root test is actually a good candidate for this kind of series. So when you have this to the n power, so that would suggest that use the root test, okay? How about we do it together, this one? So we're going to use a root test. So I'm going to take the n root of this absolute value of an. And what does it equal to? Did you just say that the n root and the n power here, they cancel? So what do you have left? This one inside? Yeah, the absolute value of that. And it is already positive, so you don't need the absolute value. But I think just to be safe, yeah, it's a good habit to put the absolute value there. So then you will have 2n plus 3, 3n plus 2. This is always positive anyway. So we can actually drop the absolute value here. Now I'm going to take the n go to infinity. What does it go to?
1.
Did you say 1? 2 over 3, yes. Yeah, it's not 1 now this time. Look at the dominating. Okay. So it's 2 over 3. Yes, go to 2 over 3, which is less than 1. Then by the root test, this series over here converge or not? Converge? Absolutely. Yeah. Not just converge. Absolutely. Okay. I like this. Very positive, strong thing. Absolutely. Okay. So this series over here itself, it converge. Absolutely. All right. Now that will conclude 11.6, and I have a little thing for you to read. Read page 719, rearrangement.